Okay, so I have a trimmer, and it's got a long handle like this, and it's got a string that comes out of it, right?
I think it's upside down for us.
There we go. How about if I do it this way? How about if I go like that? That's better, isn't it?
Yeah, that way works. Mm-hmm.
Okay, so now what I want to do is I want to pin this one. Hold on. Come here. Pin it. And okay, so when the trimmer is not running, you can see the cord. You can see the string. But when it is running, all you see is the wand, and maybe you see some bits of grass scattered around.
Yep.
So I want you to think, Kevin, for just a second. Imagine that I'm talking about atomic structure, and I've got some sort of axis, and I've got the nucleus in the center. And I'm trying to locate where those electrons are.
Mm-hmm.
We can't see the electrons, but we can know that they're there. Just like with the string trimmer, we can't see it because the string is whipping around so fast, but we know it's there.
Mm-hmm.
The way you're saying that makes me think that didn't make any sense to you.
No, that makes sense. That we can't see it, kind of like the electrons in an atom, is what you're getting at, right?
Yeah. So I think my point is something along the lines of, when it comes to atomic structure and you think about electrons in orbitals, we don't know where the electron is at any particular time, but we know that they're there. Just like with the trimmer, we don't know where that string is at any particular time as it's whipping around there. But if we had to make a guess, we would say, yeah, we know that string. It's somewhere just inside the cut, right? It's not out here somewhere because we've got no evidence of it being out there. And so probability speaking, that string is somewhere inside that circle.
Yes.
Is that better if I say it like that?
Yeah, that's a lot. I think that's very clear.
Okay, I'm picking you back outside again. Hold on a second. So this isn't related to atomic structure. This is really related to how comfortable people are with mathematics. So
Okay.
This trimmer, if I flip it around here, when I turn it on, the speed of the engine is about 5,000 revolutions per minute. And so then I think to myself, if the engine's going 5,000 revolutions per minute, when I have this thing running, how fast is this cord moving? Any idea about that?
I would guess about the same speed as the engine, maybe a little slower.
Okay, maybe a hair slower, but the gearing is such that it goes about the same speed. So what I'm going to show you is, look, if we take this tape measure, or if I measure the circle across it, you can see, maybe you'll be able to see. You'll see it's about 8 inches to the center. So it's got a diameter of about 16 inches.
Mm-hmm.
Okay, now we go back inside. Hold on a second.
Okay.
Oh, wrong one. Sorry. There's lots of opportunities to take pieces out of this. Oh, still the wrong way up. That's better. Okay. New piece of paper.
Now we're sideways.
Yeah, okay. So we know that it's 16 inches diameter.
Yep.
That's showing up?
Yes, it is.
And we know that it is, or we think it's about 5,000 revolutions per minute.
Mm-hmm.
Okay. No, you don't have to do this. I don't have to do this. None of our students have to do this. But if they don't get, if you don't get, if I don't get, if they don't get to the position of being able to say, hey, I could take that diameter and this speed and figure out how fast the outside of that string is going, you got, in order to do the math in this course, you better be comfortable with that kind of transition. I hadn't done this calculation until about 10 minutes ago, and I just figured out I could, and so I thought I would. So if I've got 16 inches diameter and 5,000 revolutions per minute, well, how far, if it's 16 inches across and it goes around in a circle like this, 16 inches, then the circumference is equal to pi times the diameter. 3.14 times 16 inches. So it's approximately 48 inches. So far, so good?
So far, so good.
So I know that it's going to go 48 inches every time it goes around. So it's 48 inches for one revolution. Fair enough?
Yep.
And I want to know how many miles per hour that is, right? We're doing the same dimensional analysis that we did before.
Looks like it.
I don't think you've ever done this. I've only ever done it once before. I don't think any of our students necessarily have done it. But if they can't get to the point where they say, yeah, I can convert that to this, then they're in trouble. So they got to really practice until it's really comfortable. So I know that 48 inches, and I got to get to miles. Well, I don't know how many inches are in a mile, but I know that it's inches to feet. And I know that it's 12 inches in 1 foot.
Sounds good.
So that'll take care of the inches, right?
Mm-hmm.
What else? Oh, feet to miles. I do know what that is. So that's going to be times feet and miles. This was the one. So this is 1 mile is 5,280 feet. Drop my pen. So that will take care of the feet. So I've already got miles, and miles is on the top, so that's promising. And so I've got to get I got to get rid of revolutions and get to hours. So apparently it's 5,000 revolutions in 1 minute.
Mm-hmm.
So that'll cancel out my revolutions, and then I got to get from minutes to hours. So I want minutes on the top, hours on the bottom, 60 and 1, and I'm going to be there.
Looks good.
And it just so happens I did this math a few minutes ago. It's 227 miles per hour.
Ooh.
So that's the speed which that thing is whipping around there at the very outside edge. It's going a lot slower inside, right? In the middle, it's not moving anywhere near that fast because it's not traveling the same distance in the same time. But at the very outside, it should be traveling pretty close to that.
Yeah.
I was never very good at angular momentum and some of those things in centripetal forces when I took physics, but I think that's a pretty good back of the envelope.
Logic is solid. That makes sense to me.
Yeah. So that was something that I was thinking about when I was using the trimmer. Probably should have been thinking about using the trimmer as well, but I started thinking about the speed that the string is using at the outside edge when it makes that cut. You don't need to be able to do this. I don't ever need to do this. Our students don't need to do this calculation, but they do need to be comfortable enough with making these kind of conversions that they say to themselves, yeah, I can do it. It's trivial. If you struggle through it, then you need to do more of them. If you get to the point where you say, it's trivial, it doesn't need to be done, that's when you can stop. What do you think of that?
That was an interesting thought experiment.
Well, let's go back outside. I got something else I want to show you.
Sure thing.
So you saw Rebecca come home. So I wanted not to measure just the trimmer's wheels, but I thought to myself, a person could measure the tires on their car, and do the same calculation if they wanted to.
Mm-hmm.
Or they could measure the diameter of their bicycle wheel, and maybe do the calculation backwards. For instance, I know when I'm riding my road bike, I can sustain maybe 16 or 17 miles per hour, and I know what I could figure out. I could look and see what size my tires were, and I could figure out how many revolutions per minute I had my tires going on. Right?
Mm-hmm.
I do that calculation, but I could. Our students need to get to the point where they could do that, whether it be for revolutions of a tire and the speed of the bike, or whether it's the calculating moles, grams, solution concentration, all those sorts of things. That needs to become trivial. So that was my thought about that was thought number 2 on the trimmer. First one was atomic structure and the way that it represents the position of the electron around the nucleus. Second one was dimensional analysis. So here we go. So maybe you know this, maybe you don't know this, but when lots of two-stroke engines, small engines, I've got this gas can here, and can you see that it says trimmer gas?
Yes.
A 1:40 ratio of oil to gas.
Mm-hmm.
Have you ever mixed fuel for like a two-stroke engine before?
No, I have not.
Okay. So the issue is with those particular engines is that they don't have a separate place for oil to go in them to lubricate the parts, the moving parts, the way you would in a vehicle, in a car engine. And so it has to go in with the gasoline. And so you make a mixture. So in this gas can, I've got some straight gasoline, which basically came from the pump. And so I'm going to pour a little of that with one hand, no less.
Please be careful. I believe in you.
There we go. Thanks for the support. Okay, so there's just a little bit of straight gasoline. And can you see it down there in the bottom of that container?
Yeah.
And it's sloshing around a little bit.
Mm-hmm.
This This one happens to be sold for where I'm at right now for snowmobiles, but it's basically the oil that you mix in there. And if I zoom in here on the back, is that focused enough that you can see that?
No, not quite.
Okay, well, it basically tells you how much you have to put in with to make the 40-to-1 mixture. And I made a measuring cup, and on the side of this thing, where does it say here? It says 125 milliliters of this oil will make 25 liters of the gasoline. That would be 5 liters of gasoline is equivalent to the 40. The 125 liters milliliters is equivalent to the 1. But I'm just going to pour some of this into this cup as well, into the second cup. So there's the cup with the gasoline. This is the cup with the oil. Okay, can you see that as that goes in there?
Yep.
Okay. And can you see what color it is if I kind of slosh it around?
It's like a dark gray, almost black color.
Yeah, yeah. And if I take it outside, you'll see it's actually a little green.
Green? Yeah, the green.
Yeah, okay.
Exactly.
If we had a higher production facility, you would see the dark green. Okay, so now this is my already mixed 40-to-1 oil and gas mixture. Let's get that in there. I'm going to pour a little of that in there. Can you see as it goes in?
Yep.
Okay. How do those colors compare?
It's a lot lighter. It's almost in between the pure gas and the pure oil. It's a light green.
Yeah, if I go like this, and to keep them straight, I go like this and like this. Does that make it better?
Yep.
Yeah. And so we don't do this in our course, but in the next course, Chem 141, students who go on to that course will learn that you can determine the concentration of solutions based on their color. And the more concentrated it is, it's often the darker it is, and the amount of light that can pass through is correlated to that. It's called Beer's law, right? Have you studied Beer's law, Kevin?
Yes, I have.
Yeah. So that's basically an example of Beer's law, right? At 40-to-1, that's the concentration, or that's the color. That's how dark it is, right? At 100%, it's as dark as that, and at 0%, it's like the pure, clear gasoline. This one probably is actually pertinent to our students. Okay, so gasoline. When you buy gasoline in the United States and in Canada, let me turn this right. Gasoline. When you buy gasoline in the United States and Canada, you can go to 2 or 3 different pumps, and those pumps have a number on them. Do you remember what those numbers are, Kevin?
Oh, I haven't driven in a long time because I'm stuck inside.
Yeah, fair enough. Like back in the good old days. But so it might say 93, or it might say 95, or it might say 97, right? Remember those numbers?
Yeah.
Yeah.
I know what you're referencing. I just don't know what they are.
Yeah, okay, fair enough. Okay, so we're going to train you here for a little bit. So you could go to a pump, and it might say 93, or it might say, is that showing up, by the way? There's the 93.
Yeah, there's a 93.
It might say 95, or it might say 97, depending on where you buy your gasoline, what standard it is. But these are called octane ratings.
Oh.
And now you're right, octane ratings. And really what they're saying is these gasolines are as good at burning. I think in this case it's 93%, or it's the equivalent of 93% octane in terms of how well it burns and what percentage you get out of it, right? And in this case it's 95. That may not be precisely right, but it's a comparison value. So maybe it's not a percentage, but it's a comparison value. And octane, something that we may or may not do in this course, is learn how to name compounds like octane, but octane is carbon, 8 carbons. That's why it's called oct, H18. So now I know that octane is C8H18, and I know it's going in my car or in my trimmer. Octane plus some oxygen will produce carbon dioxide and water. That's probably not showing up so well. Maybe I back up a little bit.
Yep.
Right. So now there's all sorts of things we could do. We could say, we could balance this equation, which I think I would do with 2, 25. Don't ask me how I'm doing this at this point. 16 and 18. Right. So now I've got a balanced equation. I could then say how much octane do I use? 1 gallon of octane, how much carbon dioxide does it produce? Or there's all sorts of different stoichiometry, but that's what's happening inside my trimmer. That's what's happening inside my car with that particular combustion reaction. So when we do chemical reactions, we could bring this one back.
Yeah, combustion reactions are always, they seem easier to do with the hydrocarbons at least.
Yeah. Well, what I would say is that this octane is a hydrocarbon, right? There's the hydrogen, there's the carbon, right? It's a little higher up. It's not methane or propane or butane, but it's the same reaction.
Yep.
So that's what I got looking at my trimmer today.